Hello everyone and welcome in a new video in this series on computation and material science. We will resume where we stopped. Last time we stopped at the topic of interatomic potentials, and in particular we set the agenda to start discussing two-body potentials or pair potentials. And the first one of them is the so-called Lennard-Jones potential. It's a two-body potential. It's one of the two-body potentials, and it's one of the oldest and still used today. And the main purpose of Lennard-Jones potential is to describe van der Waals interaction. So there are several ways to write the Lennard-Jones potential expression mathematically, but we will write it using one of the most famous forms. So it says that the potential energy as a function of distance between two particles, it's 4 times epsilon times a big bracket that has two terms. The first is a positive term, and it is sigma over r raised to power 12, and another negative term, which is sigma over r raised to power 6. So let's take a moment and describe these terms. The first term that we see on the right, this one, which is negative, it is actually a negative term, and by convention, negative here will represent attraction. So the negative term will represent the attraction between two bodies, and we will get to that in a second, describing it later. Meanwhile, there is the positive term, and this is responsible to represent repulsion among two bodies. Now, let's look deeper at the format or the form of the function itself. The 1 over r raised to power 6, this is actually a very known result in physics. It's called London dispersion forces. London named after a person rather than the city. And it has the form of 1 over r raised to power 6. And this actually can be proven rigorously, that the attractive van der Waals interaction between two particles is actually varying as a function of 1 over r raised to power 6. On the other hand, the other term, which is 1 over r to the power 12, is really arbitrary. In fact, all what you need is any power greater than 6. For example, power 7, power 8, 9, 11, 10, 11, anything, even 13 has been used in literature. Pretty much any power that's greater than 6 is enough to reasonably represent the repulsion. Now, why the choice was made by Mr. Lennard-Jones for r to the power 12? Well, this was purely for convenience. In fact, the reason is 1 over r power 12 is the square of 1 over r power 6. So back in the old days, because of the difficulty in carrying such computations, actually, in fact, with a pen and paper, it was actually much more convenient to have it just as the square of the 1 over r to the power 6. All right, so we have a general idea about the shape of the function. Let's actually start plotting this function. So I'm going to do this plot here on the left, sorry. So let's choose a coordinate system, something like this. So this is the r, this is the interaction. Typically in atomistic simulation, we have V in units of electron volt, and the distance is typically in units of angstrom. And this will be clear when we get into more practical calculations. So if you try to plot this equation using any plotting utility, Python, MATLAB, Excel, you would get something like this. Something at very long distances is actually negative and close to 0. And as we approach to 0 distance, there is a well, and then it goes up and it really goes up very fast, quite rapidly. And this is thanks to the r to the power 12 term, which is leads to a steep or a dramatic change in the function at very short distances. All right, so let's mark few important locations on this graph if you wish. First of all, there is the well minimum, the local minimum. In fact, it is the global minimum for this particular interaction when it is among two bodies, of course. This actually happens at some equilibrium distance. We call it R naught. And R naught is the equilibrium distance between two particles. Remember, this is if you have two particles interacting only with this interaction, and there is really nothing else affecting these two bodies, then the equilibrium distance, the one that minimizes the total energy, is R naught. And one can derive this with a pen and paper. It's very simple. One has just to differentiate this expression with respect to R and equating it to 0, but we will leave this as an exercise. Instead, let's continue. The least energy for these two particles is actually negative epsilon. So it is this epsilon here. So that means actually epsilon represents the depth of the well. It represents sort of, if you can roughly speaking describe it, sort of the strength of the van der Waals interaction. And then what? There is this characteristic point where the interaction energy reaches 0, and that's actually at a distance of sigma. So sigma is the distance at which V becomes 0. It's not the equilibrium distance, but it is the distance at which the interaction becomes 0. And this is very obvious. If you substitute R equals sigma here, you get 1. R equals sigma here, this gives you 1. And then 1 minus 1, that gives you 0. And then that actually verifies what we have described. Very good. Pretty much this is the description, the graphical description of the graph. Let's actually try to calculate qualitatively, of course, another useful quantity, which is the force. If you go to basic mechanics, you will learn that the force is the first derivative of the energy with respect to position with a negative sign. So that's the definition from mechanics. So if we differentiate this curve with respect to position, let's actually graph this right here. So R in angstrom. Now the force, the units of the force, if you think about it, according to this derivative, it will be simply electron volt per angstrom, and this is actually one of the convenient units in atomistic simulation. Let's also extend this line here. And now if you do the derivative and plot this equation for the force, I will leave this as an exercise for you. You will get here a negative force representing attraction. And this you can hypothesize by looking at the slope of any tangent here. Remember, a derivative represents slope of a tangent, so it's actually positive. But thanks to the negative sign here, that eventually gives you a negative value for the force. And then the force becomes 0 right at this point. And also this makes sense with calculus, where the local minimum is the position, is one of the positions where the first derivative becomes 0. And then in this part, in fact, the derivative is negative, but because of the negative sign here, that gives you a positive force, and it's actually very steep. So that's the force curve. And following the convention that we introduced earlier, negative is attractive. That means that pretty much the interaction between these two particles to the right of this point, which is R naught, is attractive. And to the left is actually repulsive. So that means if you perturb the two bodies, so these are the two bodies, if you try to push them closer to each other, then this actually leads to repulsion. And if you try to stretch them, take them out from each other, then this actually leads to attraction. But what is the physical origin of this? Without going into details, one can really summarize the following facts. Attraction, and this is detailed in physical chemistry texts, is really due to dipole interaction. So typically, if you have, let's take something that doesn't really show any ionic nature or covalent nature, just not to or metallic nature, just to not to complicate things, take an argon atom and another argon atom. So typically these atoms are spherical in nature. Their electronic structure leads to a spherical solution, but then at some instant of time, due to fluctuations, one of these atoms might develop an ellipsoidal shape and an instantaneous dipole moment, where some of the charge is, let's say, positive in some region and negative in the other region. So this is definitely where the nucleus is predominantly located, and the other where the rest of the electrons are located. This intrinsic dipole induces dipole in the other argon atom, leads also to this shape. And eventually, this leads to attraction and leads to the 1 over r to the power 6 term that we said, the London dispersion forces. Again, this is not intended to be a detailed description. It's just a quick summary for the reason of the attraction. Meanwhile, the repulsion, this is when you bring the two atoms very close to each other. So let's remember, when you bring the two atoms very close to each other, there is repulsion. And the reason for this repulsion is the overlap of electronic clouds. Remember, if this repulsion was purely Coulombic in nature, it would have been represented as 1 over r interaction, so simple Coulomb repulsion. But this is beyond Coulomb. Well, the origin is, of course, related to Coulomb. Remember, these electrons are negative species, but their attempt to overlap leads to a quantum description that's beyond 1 over r. It's way beyond 1 over. When I say way beyond, it's much stronger than 1 over r. And that's why 1 over r power 12, or any power greater than 6, is reasonably good description for this repulsion. Now, in terms of consequences, this repulsion is very important because it gives density to matter, or otherwise everything would have collapsed and everything would have been like one point with infinite density. So the reason why there is finite density to matter is thanks to this repulsion. Meanwhile, and let's go back to the attraction, the consequence of having this attraction is it gives cohesion to matter. If there is no attraction whatsoever, pretty much everything would disintegrate and collapse. I'd like to make one comment, because on the graphs that we described here, because pretty much all the descriptions that we provided here is assuming two atoms interacting with Lennard-Jones potential in vacuum, so there are no other surroundings. Meanwhile, in reality, there are surroundings. For example, you could have argon liquid, so a lot of argon atoms. True, every two of these argon atoms are interacting in a pairwise fashion, independent of the rest, but in totality, the overall behavior is thanks to the sum of all these two-body interactions. So that means that the equilibrium distance here, which we denoted as R naught, which is only present in the case when there are two atoms, is not the equilibrium distance when there are multitude of atoms. This is something that we will get into back again when we get into more practical exercises, but I will hint here to this fact. In a crystal, in a crystal, uh, uh, interacting with Lennard-Jones potential, typically the equilibrium distance in the crystal, thanks to the many-body effect, not at R0, but actually at a smaller distance. So that's the first nearest neighbor in the language of crystals. First nearest neighbor. And the second nearest neighbor is a little bit after Arnold or beyond Arnold. So that's the second nearest neighbor. We will get into these discussions when we do a practical exercise using Lennard-Jones potential. Very good. So far, we presented a description for the Lennard-Jones potential, but there is one little detail here. It's a practical detail. Pretty much all what we described is physical in nature, but there is a practical detail here. Typically, the interaction is cut after some recommended cutoff distance. So V is assigned to 0 after some R cut, decided by the developer of the potential, decided by the developer of the potential. What that means, so if we go back to the previous graph, for practical implementation on a computer, you cannot keep computing this interaction up to an infinite distance, because you see, it never becomes 0. It just approaches 0, but it never becomes. The developer of this potential, if you are using it from a paper or some research repo online, then it should recommend certain cutoff. So let's say this is R cut. And then the rationale here is that the value of the energy before R cut is calculated using the standard Lennard-Jones expression, while after R cut, the value is assumed 0. This is to simplify the calculation on the computer. Of course, this leads to some numerical issues, but this is really beyond the scope of a preliminary introduction into this topic. Let's continue. So we discussed this practical detail. It remains actually, if we go back here, it remains to ask ourselves, who finds, or where do we get the epsilon and sigma for a given interaction or for a given material? The answer is usually we get that from papers, from literature. So sigma and epsilon, where do we get them from? We get them typically from papers. And the authors of these papers, how did they get the sigma and epsilon? Remember, suppose you want to study something simple. You want to represent some Lennard-Jones interaction of a mixture made of argon and neon, for example. Then you should have epsilon and sigma representing argon-argon interaction, and another, let's call them 1. And there is epsilon and sigma representing argon-neon interaction. So this is epsilon 2 and sigma 2. And there is a third set, epsilon and sigma, representing neon-neon interaction. So you certainly, and obviously these are all different values. So you need to get them from papers. And research groups have actively developed several Lennard-Jones potentials to represent van der Waals interaction, for example, for carbon, hydrogen, nitrogen, oxygen, the family of biological materials. So there is a lot of Lennard-Jones interactions for them. Even people develop them for metals, although Lennard-Jones is problematic for metals, as we will discuss later, and for many, many other materials. The question is, how do you get them? And the answer is, typically, they are obtained by fitting to some experiments, as was done in the old days, or to quantum mechanical calculations. For example, you go to some quantum mechanical calculation, let's say density functional theory, which we will get to at a later stage of this course, and calculate some properties related to argon, argon-neon, neon-neon, maybe crystal lattice constant, maybe, for example, what? maybe bulk modulus of the crystal, maybe some elastic constant for the crystal of argon or neon, and so on, and then use these as a fitting to calculate the sigma and epsilon. And remember, the basic wisdom from mathematics is that if you are trying to fit two parameters, right, sigma and epsilon, you better have a lot of data. Hopefully more than two, or otherwise this is not fitting anymore, right? So you either have a set of experimental data or quantum mechanical data, and then you fit your sigma and epsilon, and you publish them, and so that other groups can use them. But then after the publication and having set of epsilon and sigma for certain material, what should we do? Should we always trust them? The answer is no. One has to test the so-called, in the language of computer simulation of material, the transferability of the potential. And how do you do this? Suppose, for example, the developers of the potential develop them to predict a correct Latz constant A, and correct bulk modulus B, and correct shear modulus G, and correct elastic constant C11 and C12. So this is a set of nice properties, and they are used in the fitting. So obviously, your potential should be capable of reproducing them to a very good quality. Now, how about other properties? For example, let's say melting point. Of course, melting point is a very, very complicated property. How your potential is good in computing it. Other properties, let's say thermal expansion coefficient. Thermal expansion coefficient. How is your material capable of reproducing it? And any other properties. Of course, depending on what you are interested in. For example, vacancy formation energy or any other quantity. So after you develop the potential, one usually has to test it first. Now let's recap and summarize what we have introduced in this video. We described our first two-body potential, which is the Lennard-Jones potential given in this format. We showed that it looks like a well with attraction at longer distances and repulsion at short distances. It's also indicated by the force, which is the first derivative with a negative sign. The attractive part goes as 1 over r to the power 6 and represents cohesion. The repulsive part is arbitrary and has to be any power greater than 6. Usually r to the power 12 is common and standard. Repulsion is due to the overlap of electronic clouds, and it gives density to the material. Meanwhile, attraction is due to dipole-dipole interaction, and it gives cohesion. For a practical consideration, let's go back to the drawing. After a certain cutoff distance, and by the way, I didn't mention this, this is typically 10 angstrom in most interatomic potential, 1 nanometer. So beyond 1 nanometer, you assume that the interaction is 0. And finally, research groups develop these potentials by fitting. In the old days, this was done to experimental data. The current wisdom is usually to fit to quantum mechanical calculations, particularly density functional theory. Once fitting is done, one has to test the transferability of the potential by calculating other properties for the material for which we develop the potential. Thank you so much, and see you in another video.